Let your shoulders drop and settle into an easy rhythm as we drift together through a gentle landscape of ideas. Tonight, we will imagine breathing alien air, not as a rush or a thrill, but as a slow, careful listening to the chemistry of distant skies, the way an ear might lean toward a lullaby. If you enjoy these tranquil journeys, feel free to like this video and subscribe so the calm keeps arriving for you. And there is a playlist link in the description if you would like to keep learning as you drift off, one soothing chapter after another. How sleepy are you on a scale of 1 to 10? You might imagine yourself lying back under a soft blanket of stars, each point a quiet lantern, all of them far away, and yet, in this moment, close enough to hold with your attention. Between you and those lanterns, there are worlds, and around those worlds, there are breaths, the invisible shells we call atmospheres. An atmosphere is simply a crowd of molecules moving together, bumping gently, sharing warmth and light and motion in a continuous murmur. You can picture this murmur as the hush of leaves in a windless garden, a whisper that goes on and on. The gentle rhythm continues. When we speak of breathing alien air, we are not imagining you stepping unprotected onto a strange landscape. We are imagining you listening carefully to the character of a sky, its colors at sunrise and sunset, the way it would taste on the tongue of a censor, the way light from a parent star would pass through it and be softened or deepened by the presence of vapor, gas, cloud, and delicate dust. You find yourself at the edge of a planet, above the horizon where star and sky meet, watching the sliver of light change its tone as it slides through the shallowest rim of air. This place, thin and quiet, is where astronomers often read the stories of alien atmospheres, letter by letter, line by line, in the very gentle script of a spectrum. An atmosphere can be a very simple mix, like hydrogen and helium holding hands in a light embrace around a giant planet, or it can be more complicated, a layered recipe of nitrogen, oxygen, water vapor, carbon dioxide, methane, and a sprinkle of other, rarer flavors. Imagine opening a window, a hair's breadth, and letting the faintest draft pass over your face. It is cool, or warm, or slightly sweet, or slightly dry. This is the sensation of reading an atmosphere at a distance, except the window is a star, the draft is starlight, and the sensation is captured by instruments that split light into gentle rainbows and trace delicate dips where certain colors have been softly sipped by certain molecules. Water vapor takes a little from the red, methane from the near-infrared, sodium removes a slender notch from the yellow. These are not dramatic bites, they are the smallest of tastes, and yet with patience checked again. The gentle rhythm continues. As you breathe slowly, imagine the shape and feel of a breath not only in your lungs, but as a whole environment around a planet. On a gas giant, the air does not end a few kilometers up. It continues slowly, gradually, quietly, until there is no clear boundary between atmosphere and interior, only a transition from thin to thick, to deeper and denser, from gas to fluid, from bright upper haze to deep cloud-laden layers, where sunlight is a story told in memory rather than a daily event. On a rocky world, the air is a veil, more fragile, more easily tugged away by a strong solar wind, or kept safe behind a magnetic field that cradles it like hands around a candle flame. The molecules are lighter or heavier. They rise and sink. They move as the star warms the daylight side and the night releases coolness like a soft exhale. Picture a world close to its star, warmed until metals can vaporize at the day side. On these ultra-hot Jupiters, the air contains species we associate with the ground, like iron and titanium, lifted gently into the high tiers of atmosphere. At night, without direct starlight, these atoms can condense again and settle, a quiet shower of particles you cannot hear. Somewhere else, a cooler giant wears woolen clouds of ammonia and water ice, layer upon layer. Each layer a different note, in a chord that spans from frigid upper light to warmer depth. On some sub-Neptunes, hazes form, delicate as breath on glass, formed by ultraviolet light, gently rearranging molecules into long complex chains that become tiny airborne grains. These grains scatter light, muting the rainbow, softening it until it becomes a pastel wash rather than a crisp pattern of lines. On a small rocky planet, the air might be nitrogen-rich, with a hint of oxygen produced by life or by the slow, steady chemistry of sunlight and breaks in mineral bonds. Or it might be an air of carbon dioxide, thick and heavy, holding warmth the way a down comforter holds heat. Or it might be sparse, a mere sigh of gas, vanishing into space when stirred. Each possibility brings a different color to the sky, with mostly nitrogen and just the right scattering. The sky is softly blue. With lots of haze, the sky turns gently orange. With thin air and fine dust, sunsets look cool and violet. You can imagine yourself standing at the edge of that sunset, not rushing, just observing, letting the color settle in your mind's eye, like a watercolor that dries without hurry. To understand these gentle skies, scientists think in layers. High above, the exosphere meets the silence of space, where atoms can drift away if they are fast enough. Below that, the thermosphere warms through the absorption of energetic light. Even lower, chemistry is a quiet conversation guided by temperature and pressure. Near the surface, if there is a surface, the air picks up hints from rocks, oceans, and life. In this layered scene, clouds find their preferred altitudes, not randomly, but where the conditions ask them to gather. It is comforting to picture the specks of salt, of mineral vapors that cool into glass-like grains, even clouds of iron in the hottest skies. Rain, when it falls, can be water or methane or something more exotic, and the sound of it in your mind's soft imaginings is always gentle, tapping like fingertips on a tabletop. The gentle physics behind this comes from balance. Warmth wants to rise. Coolness wants to sink. The planet spins slowly or quickly, tugging air sideways. Pressure changes softly with height, making the air thinner as you climb. The scale of that thinning depends on temperature and how heavy the molecules are. In warm, light atmospheres, the thinning is slow and the air extends high. In cooler, heavier atmospheres, it is more compact, pressing close to the ground. You can imagine the air as a delicate scarf that either floats high or wraps closely around the world, always subject to the soft push and pull of light and gravity. As light streams from a star, some wavelengths interact with the molecules in the air. Water catches certain reds and near-infrared tones. Carbon dioxide listens to other bands. Methane prefers still others. Ozone, when it is present, holds on to ultraviolet and some of the blue and far red. Sulfur dioxide, if it appears, leaves its quiet letters too. And sodium and potassium, when they are in the high air of a planet and not bound into solids, make slender notches. Each molecule is like a tuned instrument. With notes it always answers. The spectrum of a planet's atmosphere, then, is a soft orchestra. There is never a crash of cymbals, only sustained notes that blend to make a character you can learn to recognize. The gentle rhythm continues. Sometimes scientists look not only at a planet during its transit, but also as it moves behind its star, when the star alone is visible. The tiny difference tells a story about the planet's own glow. Warm air emits softly in the infrared, and by measuring that steady warmth, astronomers trace the planet's dayside and nightside temperatures, the width of the twilight band, and even the presence of winds that carry heat from one half to the other. Winds can be fast, yet in this picture they feel like a steady current, an even conveyor that moves warmth along. With long, unhurried observations, patterns emerge. A slightly warmer region shifted east, suggesting a super-rotating jet, or a gentle dip where clouds are abundant and reflect light back to space. Imagine a world orbiting a small, cool star, a red dwarf. The light is redder, the day cooler to the eye, and the planet may keep one face always turned to the star, like a person sleeping on one side. One hemisphere has an endless sunrise, the other an endless sunset, and between them lies a circle of eternal twilight. If the atmosphere is thick enough, it can circulate and share warmth, preventing the air from freezing on the night side. If it is thin, the night side can become a place of slow, quiet frost. In your imagination, you stand at the twilight edge, where the star is always low, and the sky is layered with delicate gold and deep, steady indigo. You breathe with the planet in this gentle picture, noticing how the light never grows harsh and the shadows never fully claim the sky. processes shape the air's story over long times. Volcanoes, for instance, exhale slowly over eons, releasing carbon dioxide, water vapor, sulfur compounds, and other species. Rocks and oceans absorb, exchange, and store these gases. On some worlds, a carbon silicate cycle might regulate the air's thickness, balancing the greenhouse effect, not in a dramatic punctuation, but in a slow drift that keeps the climate within a comfortable range if the conditions are kind. On others, plate tectonics may be absent, and the air evolves along another path, guided by bursts of volcanism and the quiet weathering of rock. Everything takes time. The timescales are so long that thinking of them invites you to loosen your own sense of urgency and allow the mind to float. The gentle conversation between light and air, rock and ocean, can also involve life. On Earth, oxygen is abundant because of life, and methane at present is a minor player that nonetheless tells a story of ongoing biological and geological processes. In the atmospheres of distant planets, combinations of gases may whisper similar hints. Oxygen with methane, in the right amounts, can suggest a delicate balance that without constant input would drift away. Nitrous oxide can be a soft signature, yet there are always other possibilities. Non-biological chemistry sometimes mimics these patterns. Photochemistry can make oxygen by splitting water and allowing hydrogen to escape. Methane can arise from serpentinization or from comets. Careful, patient interpretation is the rule, and it is a soothing rule because it values steadiness. No single line in a spectrum tells the whole story. Many together build a portrait. Among the most restful images to hold is that of a beam of starlight passing through the limb of a planet and being changed just a little, gently, like light through a thin curtain. With a telescope such as the James Webb Space Telescope, or with the watchful eyes of Hubble and Spitzer before it, and with the promise of large ground-based telescopes in quiet mountain air, this altered light is captured and set down. Each observation is a careful breath taken by the scientific community, a slow breathing in, a slow breathing out. Data are not opinions. They are the shapes that reality takes when coaxed into a pattern we can write down and share. Scientists then fit models to these patterns, not as a race, but as a meditative exercise, trying combinations of temperature, pressure, clouds, and chemicals, finding which just a visual surface effect. It has consequences for climate, because a sky that reflects more light keeps the world cool, while a sky that lets light in and traps warmth beneath through greenhouse gases brings a little extra gentle heat. On some planets, clouds high in the atmosphere reflect starlight and make measurable dips in phase curves. On others, heat flows upward from deeper layers, and the air radiates quietly outward, balancing the energy like a scale, finding its center. Think of hydrogen, the lightest of gases. In a hydrogen-rich atmosphere, the air is fluffy, the scale height is larger, and the same amount of absorption by a given molecule can reveal itself more plainly. On such worlds, water vapor lines are often clear, and methane steps in and out with a recognizable rhythm. On heavier atmospheres dominated by nitrogen, carbon dioxide, or oxygen, the features can be more compact, subtle, layered between clouds and surfaces. In some sub-Neptunes, observations suggest that clouds and hazes obscure the deeper view, turning would-be sharp features into broad, gentle swells. These are not frustrations. They are part of the character of those skies, and they invite new methods, longer stares, and very patient calibration. It can feel restful to hold simple pairings in mind. Hydrogen and helium are light and ancient. Nitrogen is stable and quiet, a backdrop gas. Oxygen is reactive, eager to bind, and on Earth it blooms because of life. Carbon dioxide is efficient at catching warmth, and at high partial pressures it can raise a planet's surface temperature to states that alter cloud decks and make new steady patterns. Methane and ammonia offer stories of cold places and deeper chemistry. Sulfur compounds speak of volcanism and illumination by ultraviolet light. These names are gentle here, simply labels we use to keep the mosaic organized. You do not need to memorize them. Just let them pass before you, like birds flying slowly across a calm sky. Within this calm picture, the edges of atmospheres matter. At the very top, some worlds lose gas steadily, atom by atom to space. Ultraviolet light warms the highest layers, and atoms drift away like dust lifting on a breeze. Helium has been observed escaping in this way from some exoplanets, leaving a delicate signature in a narrow band of near-infrared light. This is not a dramatic escape. It is a quiet leak that over billions of years can reshape an atmosphere, taking a sub-Neptune and drawing it down toward a rocky super-Earth, or transforming a puffy world into something more compact. The role of magnetic fields in this story is also gentle and steady. Fields deflect charged particles, sheltering the upper air, and the shape of this shelter, this magnetosphere, is like a bubble in the wind, soothing to imagine, full of arcs and soft lines. On some worlds, the air meets an ocean, and the ocean meets the rocks below, and a three-part conversation proceeds at a slow, geological tempo. Water dissolves gases, holds them for a while, then releases them again. Rocks take up carbon dioxide cycles appear, just as regal and slow. On Titan in our own solar system, for example, a thick nitrogen atmosphere holds methane in a cycle of clouds and rain and lakes. The lakes are not dangerous in your imagination. They are simply cool, dark mirrors under an amber sky. The surface smells like wet stone and something faintly sweet in your mind's safe picture, and the rain sounds like rice falling into a wooden bowl. On Venus, the atmosphere is a very thick blend of carbon dioxide with sulfuric acid droplets forming high clouds. The story there is one of profound greenhouse trapping, and the clouds form a bright reflective cover. The air moves in a global wind pattern that circles the planet faster than the surface turns, a super rotation. If you imagine being lifted into the high cloud decks, the temperature becomes more temperate, the pressure softens, and you can imagine floating platforms drifting in a pale yellow day, instruments dangling and taking notes in a placid, unhurried way. On Mars, the air is thin and carbon dioxide is primary, and dust, fine and rust-coloured, can fill the sky and give sunsets a striking, soft blue at the last moment. None of these places needs to be dramatic to be fascinating. They are each steady rooms in a great mansion of possibilities. Think, too, of worlds where ice dominates. On Neptune and Uranus, far from their star, the upper atmosphere holds methane that absorbs red light and leaves a serene blue behind. The deeper interiors, in theory, could squeeze carbon into diamond-like forms, and there are gentle stories of slow diamond rain, a metaphor for an environment where chemistry and pressure mix to make elegant outcomes. Even if the details are refined over time, the overall image is peaceful. It is a place where gravity and time make art slowly. Closer to a star, some rocky worlds are so warm that oceans of rock can exist, and the air is made from the vapor of minerals. Sodium, silicon monoxide, and more exotic species become part of the sky. On the day side, rocks slowly evaporate, and on the night side, they condense again, returning as dust or droplets. Even here, in what could be a fierce environment, you can frame it in a calm way. The cycle continues, patient and balanced, as if the planet is breathing in and out a rocky breath. Exoplanet weather can also be seen in the round, across day and night, as a planet orbits and we watch the combined light gently brighten and dim. These are called phase curves, and they tell us how reflective the planet is, how warm it becomes, and how quickly it moves heat around. In some cases, the brightest point in the curve is not exactly at the expected place, but shifted, hinting at atmospheric dynamics. Winds travel around the equator, transporting heat, and clouds form preferentially where temperatures and motions invite them to. The maps drawn from these curves are not sharp photographs. They are smooth, low-resolution impressions, like the way a room's atmosphere feels when you close your eyes and sense the breeze and the warmth without focusing on edges. In your mind, you can step into the very gentle laboratory that supports all of this. There are glass cells filled with gas. There are lamps that make light and prisms that bend it. There are detectors researchers assemble line lists, which are simple catalogues of how molecules respond to light. These catalogues, like collections of pressed leaves, are gathered over years and arranged with care. Then, when a spectrum comes in from a distant planet, the match is attempted. The match is not forced. It is coaxed, with error bars acknowledged and uncertainties presented calmly. If there is a mismatch, that is not a failure. It is a clue. The gentle rhythm continues. There is also a friendliness to the telescopes themselves. There is a sense that they are companions to the night, open petals of glass and mirrors lodging themselves in the sky to collect faint light. Space telescopes drift in their orbits, free from the shimmer of air, while ground-based telescopes peer through the atmosphere and correct for its wavy motions with adaptive optics, adjusting small mirrors so that starlight becomes clear again. Each instrument has its own personality, its own cadence of observation. Kepler kept a precise watch on a patch of sky, letting planets reveal themselves through tiny dips as they crossed their stars. Tess scans bright, nearby stars, offering worlds that are easier to follow up with detailed study. James Webb gathers the longer wavelengths, absolutely ideal for gently reading the warmth and water features of exoplanet skies. Large telescopes on the ground, with high-resolution instruments, read fine lines in the spectrum, including the faint impressions of molecular rotation and vibration, and by cross-correlating with models, they pull out the songs of molecules from the noise, like finding a melody in the middle of the hush of evening. If you let your imagination drift, you can stand in an alien meadow that you know you cannot actually visit, and you can simply pretend to breathe. The air is cool and carries the clean, faint mineral scent of frost, or it is warm and smells of a not quite earthly rain. Maybe you sense a hint of ozone after the gentle passage of high light through the air. Maybe a far-off ocean offers a tang you recognize as comforting. The colors in the sky around you are muted pastels, and a pale sun sits low or high depending on the planet's axial tilt and orbit. You know this is an imagined place, that the reality is data and models, but the sensation helps anchor the story in your senses, which welcome the softness. On many worlds, ionized layers form high above, where the atmosphere meets energetic light. These ionospheres glow softly. Auroras may appear where charged particles slide along magnetic field lines. They hang as slow draperies in the polar sky. Even without a word, they tell of flows and balances. On a planet orbiting a quiet, steady star, the auroras might be gentle and occasional. Around a more active star, they might be more frequent. But even then, in this calm narration, their presence is a slow pulsing. The way swells on an ocean take time, rise and fall, repeat and soothe. Chemical stories unfold softly across the sky as well. Photochemistry begins when light splits molecules, and then the pieces reassemble into something new. Water split into hydrogen, and hydroxyl may participate in cycles that include ozone and other oxygen species. Carbon-bearing molecules change partnerships, becoming carbon cyanide, and more. Sulfur drifts through its own set of elegantly named partners, making sulfur dioxide and beyond. Each reaction has a pace, and in the temperature and pressure of an atmosphere, these paces line up into a choreography. Some reactions are quick, others take longer, like leaves taking months to turn colour. The whole network is a tapestry and never a scramble. It is worth lingering on the topic of clouds and hazes, those most visible and yet often most confusing storytellers. Clouds form when a vapour reaches saturation, when it is ready to settle into droplets or crystals. This can happen with water, but in the very cold or very hot, it happens with other species as well. The particles can be tiny spheres or intricate aggregates. They can grow and fall, or remain suspended. Even their shapes affect how they scatter light, how they reflect, and how they absorb. Hazes are a different class, formed when photochemistry leaves behind complex macromolecules that stick together into very small grains. Hazes tend to mute features in spectra, adding a soft veil. In this story, every veil is a clue. Scientists sometimes treat clouds with simplified models as even layers that block or haze, and then gradually add detail as data improve. There is no impatience here, only a steady march toward fidelity. On the subject of habitability, the conversation remains slow and careful. A planet that could allow liquid water at the surface is one kind of hopeful place. A planet that maintains water over long times, thanks to a stable climate and gentle cycling, is another step more conducive. Add to this a friendly star whose light is steady over long periods. Consider the presence or absence of a protective magnetic field, the thickness of the air, the abundance of greenhouse gases, and the degree of clouds. All of these contribute to the quiet mathematics of average temperature and seasonal swings. If a planet orbits a small star and is tidally locked, the way air circulates matters a great deal. With enough air, heat is shared and the day-night contrast is softened. With too little, the planet can gather frost on the night side and lose its water to cold traps. None of this is dramatic in our picture. It is like watching a season pass. It is like white breath rising in winter and slowly disappearing. In the past few years, observations have offered tender, precise insights. Carbon dioxide has been identified clearly in the atmosphere of a warm gas giant, a gentle confirmation that the methods work as expected. Water vapor has left its marks in many worlds. Sulfur dioxide has been seen where photochemistry in ultraviolet light creates it, a demonstration of how sunlight participates in shaping the sky. Helium has been detected escaping from some worlds, a little leak that tells us that the upper layers are active in their own quiet way. Methane has appeared in some observations, and in others it has remained hidden, suggesting that temperatures, metallicities, and chemical networks differ from world to world. These are calm, steady steps, and they are abundant, like the sound of a distant brook that keeps going as you rest nearby, eyes half closed. Sometimes an observation yields less than expected, and that, too, is informative. A transit spectrum such flats are not empty. They imply a veil, and they tell us that to see beneath, we need different wavelengths, perhaps longer ones that peer through, or shorter ones that are scattered differently. In this way, even the absence of certain marks becomes a gentle kind of presence. You can also imagine a planet's breath as a mixture of isotopes, where heavier forms of atoms show up in slightly different counts relative to lighter ones. Ratios of deuterium to hydrogen, or of carbon-13 to carbon-12, can reveal the history of water loss or the temperature of formation. These are very delicate measures, but they are possible, and they add flavor to the portrait. Every element is a family. Every molecule is a story within that family. The gentle rhythm continues. Consider the subtlety of line shapes too. A spectral line is not infinitely thin. It broadens with pressure. It broadens with temperature. It broadens with wind. High-resolution instruments can read these broadening signatures and infer something about the air's structure. There are cross-correlation techniques, where a model spectrum is slid past the observed one, and the alignment is checked again and again until the correlation peaks. The mathematics behind this is like sliding two combs past one another until the teeth line up, a mechanical image that feels simple and calm. There is comfort in tools that work this way, in repeated motions that lead to understanding. Far from being static, atmospheres have seasons and cycles. Even a tidally locked planet can experience slow variations as stellar activity rises and falls, or as volcanic episodes release more material for a time. High clouds can come and go, altering how much light is reflected. Photochemical hazes can gather and then thin as the balance of light and gas flows adjust. The timescales vary from hours to years to millennia. In our soothing story, it is enough to sit at one timescale for a while, then lift your eyes and consider another, knowing that each one is a pattern overlaid on another pattern, all of them looping gently. The interplay of chemistry and condensation leads to rich images. On a hot gas giant, titanium oxide and vanadium oxide, if present in the air, can absorb light and warm higher layers, making temperature inversions where it is warmer above than below. This shape of the temperature profile then alters the emitted light, and with calm observation, the inversion can sometimes be seen. On cooler giants, without those absorbers, the temperature may simply decrease with height until clouds and hazes modulate the gradient. On even colder worlds, ammonia and water clouds condense in distinct tiers, and the edges of those layers are smooth, not sharp, feathering into one Let your breathing match the imagined breathing of a world. In, a slight brightening of day. Out, the onset of evening. In, a mild warming. Out, a sweet slow cooling. The gentle rhythm continues. Let us return to scattering, because it is a comforting idea. Rayleigh, scattering, the kind that gives an earth-like sky its blue, favors small particles and short wavelengths. Scattering, by larger particles like droplets or larger aerosols, is less selective about colour and often makes the sky appear whiter or more milky. These are not rival stories. They live together. In a planet's twilight, you may see the signatures of both, with blue light arcing high, while the horizon glows soft and pale. The precise balance tells a scientist about particle sizes and number densities. To you, resting and listening, it is simply a way to colour the scene. In high, thin air, where atoms can drift free, a planet makes a boundary. This exosphere is a very patient place. Particles in the topmost ranges occasionally have enough energy to escape. Over time, this process can reshape the entire atmosphere. Lighter molecules leave more readily. This is why hydrogen and helium can be rare in the upper atmospheres of some small worlds and abundant in gas giants, where gravity holds them gently but firmly. Hydrodynamic escape can occur when light from the star pours energy into the upper atmosphere, lifting it like a hot air balloon. The physics is present, yet in our calm tone it becomes a rising and a floating, a slow loss that slightly changes the mix of gases below. We can now imagine the quiet collaboration of disciplines that make this field so rich. Astronomers gather light, chemists measure spectra in the lab, geologists think about crust and mantle, oceans and minerals. Climate scientists bring models of circulation and radiative balance. Instrumentation engineers design detectors and calibration systems that hold steady under the strain of space and mountaintop nights. Data analysts test methods, remove systematics, and check results with validation datasets. This is a large, gentle choir. Each voice is soft, but together harmony fills the evening. Many famous exoplanetary names come with soothing associations when placed in this quiet setting. The TRAPPIST-1 system, for example, holds several rocky worlds near a small star, each one a potential story. Even as observations refine our expectations, sometimes revealing thinner atmospheres than hoped, or compositions that lean toward heavy molecules, the overall feeling remains one of patient discovery. LHS 1140b has been suggested to be a particularly interesting case, perhaps with a substantial amount of water or a gentle mixture of air and ocean. A world that could be more than just rock. K2-18b appears to have water-bearing air and is larger than Earth, perhaps a mini Neptune or a water-rich world. Interpretations evolve, but the pace to our ears is slow and pleasing. WASP-39b carries in its light the clear prints of carbon dioxide, water, and photochemical sulfur species. A warm sky gently reorganized by light is offset. This is measured calmly in phase curves and in the shapes of spectral lines. On temperate rocky worlds, subtler circulations appear, with cells that resemble Earth's Hadley cells, where air rises near the warm regions, flows aloft toward cooler areas, and subsides gently, closing a loop that can extend from equator to pole. The Coriolis effect, a product of rotation, curves these flows into bands. The result is not a tangle, but a series of sweeping, broad patterns. You can picture them as silk ribbons laid across the surface, parallel yet responsive to the contours of land and sea, if there are continents and oceans. On terminators, the line that separates day from night, there are subtle thermal gradients that can host specific cloud formations. High-altitude mists may gather there, making transmission spectra more muted at certain wavelengths. Observers build models that allow the day side, night side, and terminator to have different temperatures and cloud properties. They then fit the data to these models, not with a snap decision, but with long, slow inference, using methods that wander through the possibilities and give back a set of likely combinations. You can breathe in and feel a quiet satisfaction at how patient these methods are. There is no demand for a single tidy answer. There is a preference for ranges, for uncertainties expressed with care. When star and planet align just so, a secondary eclipse occurs, and for a brief time, the planet's own glow is hidden as it passes behind the star. The comparison tells you how much the planet emits or reflects on its day side. When the eclipse ends and the planet emerges again, the return of its light is like a soft exhale, a warmth felt again on a marble floor warmed by sun. Emission spectroscopy during these moments reveals temperatures and sometimes the presence of inversions. Reflectivity, or albedo, becomes measurable, and cloudiness can be inferred. Everything learned is a facet of the same steady gem. The color of alien skies is a favorite piece of gentle imagination. A thick methane haze sky could be warm amber. A hydrogen-rich sky with high, thin clouds could be powder blue with pearly highlights. A nitrogen-dominated air with dust like Mars might be tawny, with sunsets that shift to turquoise. The only limit here is the gentle respect for physics and for observation. You can let your mind walk through a sunrise rooted in soft orange, or a noon that feels like an old photograph. The imagination is a companion to the data, not a replacement, and it helps keep the science human and comfortable. It can also be soothing to revisit the idea of breathing itself. If you imagine breathing alien air, do so with the thought that on most worlds, a human lung would not find it safe or sufficient. But here, in the safe room of your mind, you can pretend that there is an interface, a subtle filter, a membrane that lets you sense the quality without taking the risk. You can sense the humidity, the temperature, the texture, and the weight. You can imagine an exosuit that makes the air comfortable inside and lets you lift the visor enough to sieve the sense of a world in whispers. They are mineral and delicate. There is no sting. There is only knowledge travelling through your senses. first drops arrive. At the edges of this field, there are gentle technological promises. Space missions designed to study exoplanet atmospheres more systematically are planned, with instruments tuned to measure molecules in the infrared and visible, to map cloud properties, to distinguish between reflective and emissive contributions. Ground-based giants, with mirrors large enough to bring in more light and with high-resolution spectrographs, will read narrower lines and tell wind speeds and rotation rates. Coronagraphs and star shades, devices that block a star's light so that the planet nearby can be seen directly, are drawn in careful engineering renderings, each detail addressed slowly and thoroughly. When these systems fly or are built, they will not make the night louder, they will make it deeper. Then there is the story of disequilibrium, one of the quieter but most intriguing concepts. An atmosphere in perfect chemical balance under given conditions would settle into certain ratios of gases. Life, geological activity, and photochemistry can keep it away from that balance. This departure is a signature of ongoing processes. On Earth, oxygen's abundance is such a signature. Methane's presence in small amounts is another. Detecting and interpreting disequilibrium in an exoplanet's air requires us to know the temperature profile, the mixing rates, the boundary conditions at the surface if there is one, and the illumination. With patience, models can be built that simulate these conditions and predict where the atmosphere will land. When reality deviates, the deviation becomes a clue. There is also a deep comfort in the timescales over which atmospheres evolve. Billions of years can pass as light and air play their game of give and take. During this time, stars age and their light changes slowly. Planets lose heat from their interiors. Tectonics may start or stop. Oceans may form or be lost. The air keeps its record, sometimes in isotope ratios, sometimes in the patterns of noble gases, sometimes in the dew of frost at the poles. When we think of our own Earth's history, we see gradual arcs from an early atmosphere likely rich in carbon dioxide and nitrogen, to a later one where biological oxygen rose and iron in the oceans rusted and settled, painting rocks with quiet layers. The great oxygenation was not an explosion, it was a sunrise stretched across ages. We can also imagine the role of comets and asteroids as tender couriers of volatiles. Early in a planetary system's life, these icy bodies bring water and organics to inner worlds. Later, occasional impacts can deliver small doses, like brief visits from old friends. The idea that life's building blocks arrive from the outer reaches is not a dramatic claim here. It is a gentle reminder that the system is connected, that the cold and the warm parts share. Slowly and steadily, the structure of a planet's interior leaves its mark on the air. If a mantle is redox rich, certain gases are favored in volcanic exhalations. If plate tectonics operate, then carbon can be sequestered and later released, dampening climate swings. If the lid is stagnant, the cycle is different. Each interior style is like a musical mode, and the atmosphere gently active. When activity rises in the form of flares or changes in ultraviolet output, it is best to imagine this as a soft flicker in our narration. It may alter the upper atmosphere, boost certain photochemical paths, or increase the escape rate for a time. Over a star's life, the overall amount of activity shifts, often quieting as the star ages and its rotation slows. In the context of habitability, this trend matters. For planets orbiting older, calmer stars, the long quiet might be a gift, allowing atmospheres to find an enduring balance. Let yourself linger on the idea of pressure. The pressure at the surface of a planet, if there is a surface, can vary from very low to very high, like the difference between a gentle breeze and a deep ocean. Pressure determines which phases of substances are stable. With enough pressure and the right temperature, water can be liquid. With less, it may sublimate. Carbon dioxide can form a frost. Ammonia can remain vapor or condense into clouds. The thought of these phases shifting is soothing. It is the same as watching ice melt in a glass or steam rise from a cup, only stretched to a planetary scale and elongated in time. There is also a poetic line connecting breathing and mixing. In an atmosphere, mixing means that gases are stirred and blended. Convection lifts and lowers parcels of air. Diffusion allows molecules to wander and even out over time. Horizontal mixing by winds smooths differences. In your own body, breathing mixes air in the lungs, bringing fresh oxygen to capillaries and carrying out carbon dioxide. It is not inappropriate to imagine a planet's air breathing likewise, simply as a metaphor, moving enough to refresh, moving slowly enough to keep layers in place. As observations reach towards smaller and cooler planets, data often become thinner and more precious. Signals are small. Noise is a companion, yet the community approaches these challenges with a style appropriate to bedtime. They co-add, they observe again, they combine results across instruments, they cross-check with independent pipelines. Small steps are acknowledged, caution is embraced, claims that are not firm are presented as possibilities. Eventually, with enough careful watching, the signal rises and becomes something you can see without squinting. When that happens, it still feels like a whisper. The gentle rhythm continues. You can imagine the near future as a widening of this soft path. Dedicated missions for atmospheric characterization will not chase drama. They will gather spectra by the hundreds. They will measure clouds and trace gases across many worlds, building a statistical understanding that soothes the mind. Patterns will emerge, such as correlations between a star's metallicity and the carbon-to-oxygen ratio in its planets, or between a planet's mass and the clarity of its atmosphere. None of these patterns needs to be surprising. They will be quietly satisfying, like aligning books on a shelf by height and watching the line become smooth. It might feel nice to revisit specific molecules and let your attention rest gently on each one. Water vapor is both an absorber and a friend of captures outgoing warmth and releases it again, creating a blanket effect that can be modest or strong. Methane is potent in the infrared, and in cold conditions it condenses and falls as rain on worlds like Titan. Ammonia's role is often in clouds of the colder giants, forms of ice high in the atmosphere. Hydrogen cyanide appears in photochemistry, a molecule that opens pathways to more complex organics under the right conditions. Ozone, where it forms, shields ultraviolet light and is a marker of oxygen presence and photochemical balance. Each name is familiar, each function gentle, each presence a clue. In high temperatures, molecules break into atoms, then ions. At lower temperatures, they assemble into increasingly complex structures. The beans in this stew change with heat. An ultra-hot Jupiter has air that includes fragments of molecules, and the light from its day side carries the signature of those fragments. A temperate mini-Neptune may have intact molecules and a haze that blurs the view. A rocky planet may have an air where the surface plays a major role, adding and removing gases constantly, a breathing that is fully coupled to the ground and the ocean. Imagine the measurement of rotation in a distant planet's atmosphere, detected through the way line shapes are broadened by the movement of air. The day side may show a pattern corresponding to an eastward wind, while the limb reveals a different dynamic. With high resolution, the rotation period can even be inferred in some cases. Each result is not a headline, it is a notch, a small cut on a wooden stick, a tally in a ledger that keeps time quietly and accurately. The phrase scale height can be a comfort as well. It is a measure of how quickly pressure decreases with height. In warm, light air, the scale height is larger and the atmosphere is more extended. In cool, heavy air, the scale height is smaller and the air is snug. When scientists model transmission spectra, the amplitude of absorption features scales with this height, which is why hydrogen-rich worlds are easier to read. There is logic and order here that feels like a soft song, repeatable and kind. Returning to clouds, one can think of their optical properties in a tender way. The single scattering albedo tells how likely a photon is to be scattered rather than absorbed. The phase function tells the directionality of scattering. These terms sound formal, but in your mind they are just descriptions of how light bends and reflects off tiny particles. The result creates halos around stars, soft glows, and specific patterns in the way brightness changes with angle. Observers use these patterns to infer cloud particle sizes, and over time, these inferences build a picture of cloud composition and physics. Each chosen model is tested gently, the way a hand tests the temperature of bath water. Throughout retrieval methods, the mathematical ways of deriving atmospheric properties from observed spectra are careful. They use Bayesian statistics, producing probability distributions rather than single points. They include priors that gather what we already know, machinery recovers the originals. They compare results across different teams and different codes. All of these practices are like the rituals you build to fall asleep, familiar and comforting. You know what comes next, and this predictability is a balm. The interplay of aerosols with chemistry extends into long time scales. Aerosols can catalyze reactions on their surfaces. They provide locations where gases can meet and transform. In sulfur-rich environments, they become vehicles for cycling between gas and condensed phases. In water-rich environments, they become the seeds of raindrops, and their number and size determine cloud brightness and persistence. In redder light from cool stars, photochemical rates may shift, and the outcomes produce different haze colors and densities. Everything is a function of everything else, and yet the consequences are not chaotic in the everyday sense. They are orderly because nature loves patterns, and patterns are restful. Imagine also the quiet helps we receive from planetary occultations of background stars. Sometimes a planet in our own solar system passes in front of a distant star, and the starlight, filtered by the planet's atmosphere, tells us about winds, temperature, and layers. Exoplanets are too far to arrange such coincidences easily, but they give us the conceptual template. When we measure light across an exoplanet's limb during transit, we are doing something similar. The idea that we can learn about winds and haze from a change in brightness during such a passage is a gentle joy, like learning the character of a friend from the way they walk. Over and over, the theme returns to balance. Energy in, energy out, absorption and emission, evaporation and condensation, escape and retention, mixing and separation. These pairs create the full story. A planet finds its climate within these balances, and small shifts over long times can move the climate from one stable pattern to another. In science, these stable points are called attractors, and they are places where the system likes to rest. When a system is in one of these resting places, small disturbances are smoothed away. The notion of a resting place is perfect for a sleepy mind. It means that the natural world, in its vastness, also craves equilibrium. The human element, the way we approach the unknown, is also worth a soft look. Students join research groups and learn the craft. People teach one another how to calibrate a detector, how to clean a spectrum, how to write code that explores a parameter space with patience. Papers are written. The language is precise but not harsh. Results are compared. Sometimes new work revises old interpretations, not with drama, but with gratitude for the refinement. The work itself becomes like a gentle tide, never fully stopping, always cresting in small waves of understanding and receding, leaving clear sand. As you linger nearer the end of this quiet journey, let us wind back to the sensation of breathing. You can feel your own breath, unforced and slow, a signal that your body is ready for rest. Imagine that, far away, on a world hidden by its stars' glow, an atmosphere is doing the same, with winds and cycles that late afternoon. Dust motes drift, golden in the beam. The room is quiet. Somewhere a clock ticks. This is the feeling I hope follows you into sleep when you think of exoplanet atmospheres. They are not spectacles that demand your attention. They are little rooms of physics and chemistry lit by the softest lamp, rooms to visit when your mind wants something steady, detailed, and undemanding. You may also remember that the phrase breathing alien air can be a promise to stay curious, to keep learning gently. Each new observation is another measured breath, and over time, the lungs of knowledge expand. Our instruments will improve. Our understanding will deepen. The worlds will keep orbiting quietly, their skies always busy, always patient. The gentle rhythm continues. As you return to your room, to your own safe air, let yourself sink into the present. Your pillow supports your head. Your blanket holds in warmth. The world around you is quiet and familiar. The night is a shelter. If you enjoyed this slow journey, consider subscribing